Hello. In this video, I plan to talk about some of the observations that archaeologists make on chipped stone tools, cores, and debitage, the flakes, whether used or not, that were removed from cores. Here I want to emphasize those kinds of observations that help us figure out the technological choices that flint knappers made, such as when to abandon a platform on a core and switch to a new one, or how to break a blade into useful segments. There are many other observations that one could make, including ones related to tool use, but here we'll focus on the reduction sequence and the Chaîne Opératoire.
One approach to stone tools has a really long history in archaeology. The typological approach involves classifying stone tools mainly by their shape, and often associates those shapes with particular functions. Notably, the typological approach was instrumental in helping to track so-called cultures through space and time. Although this approach is still with us, there are other approaches that supplement it and to some extent replace it. One type of lithic analysis involves trying to determine the sources of raw material, whether that be flint in a chalk face or cobbles in a stream bed. But sourcing raw materials works particularly well when the materials are igneous, especially obsidian. Archaeologists in the 1960s discovered that the chemical compositions of obsidians could be a clue to their sources. One convenient method for analyzing those compositions is X-ray fluorescence analysis, which today is even available in portable equipment, such as this Bruker device, which can be handheld or mounted on a stand. X-ray fluorescence yields a spectrum, which is kind of like a histogram, with X-ray energy along the x-axis. Peaks in the spectrum correspond with the distinctive energies of transitions in the electron shells of atoms that happen when X-rays strike the specimen. In this spectrum, this peak at left is the K-alpha peak for iron, while this one is the K-alpha peak for rubidium. Many smaller peaks in the spectrum come from trace elements like zirconium and niobium. When we plot statistical summaries of those compositions on a scatter plot, we find that obsidians known to come from the same source fall within the same clusters on the plot. These so-called fingerprints provide a basis for identifying the sources of artifactual obsidians whose source is unknown. This very large flake, I think struck from a large lavawa core, shows some of the main features to watch for on a flake. The point of percussion is here, and the bulb of percussion occurs on the ventral side directly above it. The first thing you need to know is how to orient a flake. The flake is oriented with the platform at the bottom, so that the point of percussion, the place where the hammer struck the platform, is where you see the arrow. With the dorsal side, which corresponds to the exterior of the core, upwards, we define the left and right edges of the flake. For the ventral side, shown at right, the left and right edges are of course the reverse. Archaeologists describe the portions of a flake with the proximal end, the one closest to the platform. The end farthest from the point of percussion is the distal end, and the remainder is the medial portion. When a flake is broken, the part that retains the platform is called the proximal portion. A medial portion is broken on both ends, while a distal portion retains the termination, the point farthest from the point of percussion. Features on the dorsal side of the flake include flake scars, where other flakes have been removed, and the raised boundary between two flake scars is called an aris, or dorsal ridge. Some flakes show traces of cortex, the outer layer of a nodule, and flakes that have been selected for use as tool blanks may show retouch, tiny flake removals either to refine the shape of the edge or to sharpen or dull the edge. On the flake's ventral side, one of the most notable features is the bulb of percussion, a raised or bulging area close to the point of percussion. Sometimes there are also small radiating crack-like features called hackles, and something that looks like a small flaking scar called an érailleur. The ventral side often also shows ripples radiating like waves away from the point of percussion. When making measurements on a flake, it's important first to identify the point of percussion and the plane of the platform. Treating that plane as the base of a rectangle that tightly encloses the flake provides the basis for two measurements of length and width. A line that's perpendicular to the platform and extending from the point of percussion is the axis that's the basis for axial length, as well as axial width, halfway along the axial length and at right angles to it. By contrast, maximum length is simply the longest line segment that you can fit within the plan of the flake, which is identical to the diameter of the smallest circle that will enclose the flake. A line segment halfway along the maximum length and at right angles to it is the width at half maximum.
One analytical approach that's particularly common in lithics analysis, but is found in other branches of archaeology as well, is called the Chaîne Opératoire. It's an approach that focuses on the strategies, decision-making, and gestures of the ancient people who made things, including lithics and pottery and so on. It tries to reconstruct the sequence of operations in their production of these artifacts, but not just producing a sequence, but also tries to figure out what were their strategies in pursuing that particular sequence.
One of the implications of the Chaîne Opératoire is that some of the products of flintknapping, rather than necessarily being distinct types in a typological system, could represent different stages in the manufacture, use, resharpening, and recycling of the tool. Archaeologists who use the Chaîne Opératoire conceive of technology as a subsystem of culture, and which in turn has its own subsystems, and which interacts with many other subsystems. For example, the subsystem for making stone tools might in turn depend on the subsystem that makes antler hammers, and the subsystems that make the hafting materials for the tool. They also analyze these systems by identifying a series of steps, or an operational sequence, that outlines the series of decisions and activities and processes that a toolmaker followed while making a tool. Such sequences can have feedback loops. For example, accidental breakage could result in a tool or a core being recycled as a new kind of core. Such sequences vary considerably, but typically include acquiring raw materials, reducing cores, selecting flakes for tool blanks, retouch, use, resharpening, recycling, and eventual discard. But an important aspect of the Chaîne Opératoire approach is that it doesn't focus only on technical acts, but also on cognitive aspects, like the flintknapper's knowledge, savoir-faire or know-how, skill, and performance, all in the context of the flintknapper's cultural environment. The flintknapper's immersion in this environment can lead to particular habits and gestures in the production of a tool. The flintknapper's knowledge, habits, and gestures can leave traces on the stone tools that we can recognize. For example, when the flake scars on the dorsal side of a flake indicate that the knapper removed all of the flakes from the same platform, we can infer that the knapper was using a single platform core. And when the flake scars are also long and parallel, we can see that the flint knapper's goal was to produce blades. When the evidence shows that the blades were removed from alternating directions, as here, we can infer that the flint knapper used an opposed platform core, probably one that was very carefully prepared. Other orientations of flake scars can indicate that the knapper abandoned a platform and then turned the core to use a different platform, or removed a large flake to rejuvenate the core. A centripetal arrangement of flake scars can also indicate the knapper's use of a prepared core, such as a Levallois core. In their attempts to infer the steps and decisions that flint knappers took, lithic analysts make a wide variety of observations on debitage, the flakes removed from a core, and cores themselves. Among the attributes they observe are the presence and extent of cortex on a flake. This can be important because the presence of cortex tells us that the flake was removed in an early stage of core reduction. One way to measure the extent of cortex is to impose a grid of dots over the flake. Of all the dots that intersect the flake, the number that also intersect cortex, here marked in red, provides a basis for estimating the proportion of cortex on the dorsal surface of the flake. In this case, it's 30%. Another observation that lithic analysts make on debitage is the type of termination, which helps us identify knapping errors. In general, a well-executed flake removal results in a feather termination, which gradually tapers to a very sharp edge, while snapping and bending fractures can result in step terminations or hinge terminations. And some kinds of knapping errors lead to plunging terminations, which wrap around the bottom of the core. Where there's retouch on a flake to make it into a tool, we can measure that retouch in a number of ways. We can classify the type of retouch on an ordinal scale, from scaled to stepped to subparallel to parallel, corresponding loosely to the skill of the flint knapper. We can also measure the invasiveness of retouch on an ordinal scale, from short retouch to long retouch, invasive retouch, and covering retouch. We can also classify the distribution of retouch on the edges of a tool on a nominal scale. Direct retouch only occurs on the dorsal side of the flake, while bifacial retouch occurs on both sides of the same edge. Alternate retouch occurs on the dorsal side of one edge and the ventral side of the opposite edge. And inverse retouch only occurs on the ventral side. But we can also measure extent of retouch on a ratio scale using a radial chart. After centering the flake on its axial length and width, we find the radiating lines that mark the beginning and end of the retouch portion of the edge, and note how many degrees those represent. The difference between those two numbers gives us a measure of the extent of retouch that doesn't depend on the size of the tool.
Archaeologists employ a wide variety of methods to determine the sources of raw materials for knapped tools, and they also make a wide variety of observations on the products of knapping in order to determine the sequence of the reduction sequence, the sequence of removals that led to the debitage and the tools that we find in archaeological deposits. Increasingly, they use the Chaîne Opératoire as kind of the unifying both method and theoretical perspective for analyzing that material, because it helps us understand not simply the sequence of removals or even the decisions behind raw material procurement, but also the strategies and gestures that were involved in the removals that led to a tool. If you'd like to learn more about this topic, you can look at Chapter 11 of my book, The Archaeologist Laboratory, available from Springer.
And some other books I find useful include these two by William Andrewski and John Whitaker, and one on the Chaîne Opératoire by Roger Grace.
And if you'd like to be alerted when I make new videos on archaeological laboratory activities, you can click on the subscribe button down below. Thank you and stay safe.